All right, thanks for watching this video. Make sure you submit your practice problems before the end of the day. So we're going to cover charge, electric fields, and Coulomb's law in this video. All right, so for this part of topic 5.1, we're going to need three equations from the data booklet. We're going to need the Coulomb's law equation. This is, again, topic 5.1. Make sure you have your data booklet out. Coulomb's law. This tells me the force of attraction between two charges, Q1, Q2. I have K. K is Coulomb's constant. Coulomb's constant can be found in front of your data booklet. R is the distance between their centers squared. So this is the distance between the center of the charges. The center of each charge. This equation should look really familiar to you. It should look a lot like the force of gravitation equation. They're both inverse square laws. We have this equation for the Coulomb constant. I'm going to erase. The Coulomb constant is given in the front of the data booklet, but it can also be calculated by 1 over, in parentheses, 4 pi epsilon naught. This epsilon naught is the permittivity of free space. This is the Greek symbol epsilon. Epsilon naught is also given in the front of your data booklet. And the last equation we're going to use, this is the electric field strength equation, E field strength equation. It tells me that this is equal to the force per charge. The charge Q has units of Coulomb, capital C, and the force is in newtons. So the electric field has units of Newton per Coulomb. Newton times Coulomb to the minus 1. All right, this might seem trivial, but we got to discuss where charges come from. In the Bohr model of the atom, electrons orbit around a central nucleus. We know that's not true, but that's just easy for us to understand. So we know that the proton has the positive charge. We will learn why later on. The neutron has no charge. We'll learn why in topic 7. And the electron has an overall negative charge. Again, we'll discuss these subatomic particles later. So then if the number of electrons and protons are equal, the atom is neutral. Removing electrons gives the atom an overall positive charge. If you add protons to an atom, you've changed what atom you're dealing with. We will not deal with removing protons or bombarding nuclei, not in this topic. And adding electrons can give an atom an overall negative charge. So positive ions are called cations, negatives anions. Okay, let's talk about electrons really quick. Although we like to consider the charge of an electron as -1 and the charge of the proton as +1, that's not their actual charge. We will be describing their charges in terms of the elementary charge E. The unit for charge is C, the Coulomb. And one electron charge, it actually has a value of 1.6 E-19 coulombs. Sir William Crookes used a cathode ray tube, seen up here, to demonstrate that electrons were negatively charged by applying a voltage. I'm not going to go into that. And also we have the physicists Robert Millikan and Harvey Fletcher did their famous oil drop experiment in 1909 to actually determine the charge of an electron. You're probably all familiar with charging by contact, but we review anyways. It's really important to note that charging up an object by mechanical action doesn't actually create charges. It's just a transfer of charges, okay? So let's say we have Albert, the physics cat, and we rub a balloon on little Albert. What's going to happen is the balloon is going to strip electrons off Albert. Albert becomes positively charged, and the balloon gets an overall negative charge, but the net charge between these two objects is still 0. Thank you, Albert. So charge is analogous to mass, except there are two different types of charges, positive and negative, as we previously learned. And unlike force of gravity, you don't just have attraction, you can also have repulsion. So like charges repel each other, two protons would try to come away from each other, and a proton and an electron would attract each other. we see here in this schematic. So we use a model that represents some of this behavior involving a physical property called charge. And plus and minus, these are just naming conventions to describe the opposite behavior that protons and electrons exhibit inside of electric fields, which we're about to learn about, and inside of magnetic fields. The nature of these charges, it's positive and negative. It's a very crude explanation. When we get to topic 7, we are going to learn about color charge, and we will use the 3-color model to describe charges, but we'll cross that bridge when we get there. Okay, so charge, just like energy, is conserved. It cannot be created or destroyed. All of these charges were created at the beginning of the universe, at the Big Bang, and so what we witness now is just a transfer, an exchange of charges. It's important to note that the conservation of charge is something that's never violated. But when we get to particle physics in topic 7, we will see where mass isn't always conserved. So no discussion of charges is complete without referencing Charles Augustin de Coulomb. He studied charges, discovered this inverse square law for the electric force F between 2 point charges Q1 and Q2, separated by some distance r. Remember that r is the distance between their centers. And he gave us this equation. It looks a lot like the universal gravitation law. Please be careful because K is Coulomb's constant. K sub B is Boltzmann's constant. Don't get them twisted. There is one more form of Coulomb's law where we replace K with 1 over 4 pi epsilon naught. Epsilon naught, permittivity of free space, 8.85 E negative 12 Coulomb squared per Newton per meter squared. We can extend Coulomb's law beyond point charges to include like spherical shells, okay? And using calculus, thank you, Gauss, one of the greatest mathematicians who ever lived, we can show or prove that a shell of charge Q acts as if all of that charge is concentrated at its center. So Coulomb's law works not only for point charges that have no radii, but for any type of spherical distribution. Just be very clear that r is the distance between the centers of the charges. Okay, this is our first practice problem. State Coulomb's law. So go to the data booklet, get this equation, F equals K times Q1 times charge 2 all over r squared. And you're going to put this into words. You need to discuss what these symbols mean, the force of attraction or repulsion. You're going to use words like attraction, repulsion, force, the constant. So just using this equation as your guide, put Coulomb's law into words. Question number 2. In a simple model of the hydrogen atom, the electron can be regarded as being in a circular orbit about the proton. The radius of the orbit is 2 times 10 to the minus 10 meters. A. Determine the magnitude of the electric force between the proton and the electron. So you will use this equation, F equals K times Q1 times Q2 over r squared. Please note that when F is negative, you get the force of attraction. When F is positive, you have repulsion. So you will have a negative charge. Get the K from the data booklet, the distance provided here, Q1, Q2 also in the data booklet. All right, we need to define now what an electric field is. So let's say we have a smaller charge Q located at some distance r from a larger charge Q. We can define the electric field strength E as the force per unit charge acting on the smaller Q due to the presence of the larger Q. The electric field strength has this equation, E equals F over Q. The units are newtons per coulomb, and this is a vector. All right, let's talk about the nature of fields and why the idea of a field even arose. So in 1905, Albert Einstein published his special theory of relativity, And pretty much he stated that no information, no particle can travel faster than the speed of light, 300 million meters per second. Thus, the Coulomb force signal, like acting between a proton and an electron, can't travel any faster than the speed of light. So the electric force back in the day was thought to be action at a distance force. This is a problem considering that whatever this signal is can't travel faster than the speed of light. This required a paradigm shift from action at a distance to the idea of fields. All right, so in the action at a distance model, if the Coulomb force signal can't propagate faster than the speed of light, the electrons trapped in the orbit about the nuclei cannot instantaneously feel the Coulomb force. You know, there's a lag between the signal transmitted by the proton and the response. So they can't adjust the motion to maintain in a circular orbit. So this is what would happen. You would see this electron just spiral off. Can rewind that in. I can't rewind it. Okay, so since electrons in orbit around a nucleus do not spiral away, a new model was adopted, the field. That means that the space around the nucleus is distorted by the nuclear charge in such a way that the electron automatically knows how to act. It gets the information from the surrounding field. So the electric field model is analogous to the gravitational field model in that you have this larger charge Q and it distorts space around it. Now this isn't the warping of space-time like with gravity. Instead, this is information around the charge, these field lines, and the electron is influenced by this surrounding field. We will talk about what this field is. It's just virtual particles that pop in and out of existence immediately around the proton. We will get into that for topic 7. But this local curvature, if you will, this local distortion of the space around the proton is how the electron is able to instantly react to the proton, maintaining its perfectly circular orbit and not spiraling away. So let's talk about polarity. Electric fields, you can have monopoles, you can also have dipoles. Unlike in magnetic fields, you can only have dipoles. Electric fields are drawn as arrows, and field lines can point into or out of a charged particle. So these are two radial fields. You need to know the difference between a radial field and a uniform field. So we have a negative charge. The field lines are directed into the negative charge. The field lines are drawn out of a positive charge. And notice that these field lines, they are not uniform. They're not uniform because the spaces between the field lines changes at different positions. So I can see that that's a non-uniform distribution. The spacing between the field lines is not even. You need to know this, and you do need to know the difference between the positive field lines, how they travel out of the positive charge, and how the field lines come into the negative charge. So do draw these, put these in your notebook. So if we bring two opposite electric monopoles near each other, their fields will interact. And what you get is something that looks like this. The field lines are enhanced in the middle, so you would actually get a strengthening of the electric field in between. This is a dipole. Notice still the field lines going into the negative charge and the field lines coming out of the positive charge. This is still non-uniform. If you look at the spacing between the field lines, this would still be a non-uniform field distribution. So the electric field lines between two like charges would oppose each other, and so you would get a field distribution that looks like this. In the middle, here, there is no field. The field strength would be 0 newtons per coulomb. The field lines oppose each other. Okay, so we have electric fields between parallel plates. Yeah, they are uniform. The field is non-uniform as it bulges out of the ends here, so this is the only place where you get like a deviation from the uniformity. But the parallel plates are really amazing because the middle, this space in between, is where we have a uniform electric field. All the space, the lines, the spacing between these E field lines are even. So a charged object placed in the middle of this uniform electric field would experience constant acceleration. And that's really useful for us because we don't want to do calculus in this class. Maybe we do, but we don't really have the tools yet. We don't want to have to deal with changing accelerations. So we can see again that the field lines come out of the positive plate and into the negatively charged plate. All right, practice problem 2. In a simple model of the hydrogen atom, the electron can be regarded as being in circular orbit about the proton. The radius of the orbit is 2e-10 meters. Calculate the magnitude of the electric field strength E and state the direction of the electric field due to the proton at a distance of 2e-10 meters from the proton. All right, so we are going to calculate the electric field strength, so you'll need to use the correct equation from the data booklet, 5.1. All right, so we will use E equals F over Q. We already have F from part A, and we have Q. Q is the constant, 1.6 e-19, and then you also need to state the direction of the electric field. It's coming out of which particle, and it's going towards which particle. Practice problem 3. The diagram shows two equal and opposite charges that are fixed in place, negative Q, positive Q. At which points is the electric field directed to the right? So at X, Y, or Z is the electric field pointing to the right. So to do this, you want to draw the field around the negative charge. Remember, it goes in to the negative. And then let's draw the field around the positive charge. So you tell me at which positions is the electric field pointing to the right. Question 4. A proton traveling to the right with horizontal speed of 16,000 meters per second enters a uniform electric field of strength E. The electric field has a magnitude of 2,000 newtons per coulomb and is directed downwards. A. Calculate the magnitude of the electric force acting on the proton when it is in the electric field. E equals you will solve then for F. Part B, in what direction does the proton begin to move as it travels through the uniform electric fields? Through the uniform fields. You tell me, look at what the direction of the field lines, where they're pointing. Where would a proton move in the electric field? Part C, if the proton were replaced with an electron, which has a negative charge, in what direction would the electron move within the field? Think about it. Question number 5. Two isolated point charges, -7 microcoulomb and +2 microcoulomb, are at a fixed distance apart. At which point A, B, C, or D is it possible for the electric field strength to be 0? Okay, so let's see. Notice that -7, it has a larger magnitude of charge than the +2 microcoulomb charge. So the -7, this charge is going to come in. The +2 microcoulomb charge will go out, and the field lines will sort of wrap around. I guess I should draw like that. And let me see. So where might the electric field strength go to 0? So we can simplify our drawings of electric fields by using top views and rays. Which of the fields A, B, C, or D has the largest negative charge, the largest positive charge, the smallest negative charge, and the smallest positive charge? So here's the hint. More lines equals greater charge, greater magnitude of charge. The uniform electric field strength inside two parallel plates is 275 newtons per coulomb. The plates are separated by a distance of 2.5 centimeters. A plus 12 microcoulomb charge having a mass of 0.25 grams is placed in the field at A and released. Label the polarity of the plates on the diagram. Polarity meaning tell me draw on the diagram which is the positive plate and which is the negative plate. And hint, look at the direction of the electric field lines. For part B, you're going to calculate the electric force acting on the mass. Be careful with part B because you have 12 microcoulomb. If you don't know what a micro is, check the data booklet. It's in the front of the data booklet. This is a prefix. Okay, for part C, you're going to calculate the mass's acceleration. So to do this, you need to figure out what is the net force on the mass. Remember, Newton's second law says that F net equals mass times acceleration. Once you get the net force, divide away the mass. Make sure to convert to the correct units. Is that SI or grams SI? I don't know. I do, but you need to tell me. And let's see, what are the forces acting on this particle? So we have the electric force, F sub E, the electrostatic force, and we also have, the object's force of gravity. I drew these arrows the same magnitude because I don't know which is larger, but the net force will be the difference between these. Divide away the mass, and then you will have the acceleration. Number 8, the diagram shows a pair of horizontal metal plates. Electrons can be deflected vertically using an electric field between the plates. Define electric field strength. So put into words what electric field strength is, and remember, whenever you get these questions on the IB exam, feel free to turn to your data booklet and put that equation for the electric field strength or whatever into words. Part B, label on the diagram the polarity of the metal plates, which would cause an electron positioned between the plates to accelerate upwards. So the electron is moving upwards. Label the polarity, label the charges on the plates. That would make sense for this scenario. Then for part C, you're going to draw the shape and direction of the electric field between the plates on the diagram. Be very careful. Remember where the field lines come out of and where they should be going into. For part D, calculate the force on an electron between the plates when the electric field strength has a value of 2,500 newtons per coulomb. Grab your equation for electric field strength. The Q, the charge of an electron, is in front of the data booklet, and then calculate the electric force, the electrostatic force. For part E, you're going to calculate the acceleration of an electron that is placed at the positive plate. I want you to ignore gravity. We will go into reasons why later. But we can get the acceleration because the electrostatic force we calculated in the previous question is equal to the mass of the electron times the electron's acceleration. I'm gonna allow you to use F sub E as the net force. Okay, where do you get the mass of the electron from? It's in front of your data booklet. So go there and check it and solve for the acceleration. For part F, you're going to explain why determination of the electron's speed at the positive plate is possible with this type of electric field distribution. Hint, hint, when the electric field is uniform, what does that mean about acceleration?